Right, this is a question based on fluid mechanics that it's recently included in AP Physics 1 from this year. It says that there's a fluid with density rho that flows through a pipe gradually decreasing diameter, as shown in the figure. On the left side of the pipe is a diameter of d naught. Sketch a graph the relationship between the velocity of the fluid and the diameter of the pipe. Okay, so I think we have to use the continuity equation of continuity is already given that the velocity is v naught when the diameter is d naught, and the equation of continuity says that a1 v1 is equal to a2 v2, where a is the area and v is the velocity. If this has a diameter of d naught, then obviously the radius is going to be exactly half, which is d naught over 2. So I'm going to say that pi times d naught over 2 square times v naught should be equal to area at any particular diameter. So pi times, let's say the diameter is d, so d over 2 square times some velocity v that I need to find. So pi and pi is gone. I'm left with d naught square over 4 times v naught is equal to d square over 4 times v. These two are gone. Velocity should be my y-axis. So let's flip the equation here. So vd square should be equal to v naught d naught square. So v will be equal to v naught d naught square over d square. That's the equation that we are looking for. Now, v and d square are inversely proportional to each other, right? So that's going to look like a rectangular hyperbola. I mean, don't go with that terminology. It will look the figure will look something like this. But we can definitely make it a little more precise by marking the axis. We can mark this as 0.25 d naught. This will be 0.5 d naught. This will be 0. I mean, can I make more space? Well, I'll try to. This is 0.25 d naught. This is 0.5 d naught, and this is 0.75 d naught. All right. If the diameter is 0.25, or let's actually find at each point. So if you want to be more precise, let's say it is half. If the diameter is half, then it makes sense that if the diameter is half, if this is replaced with d over 2, then velocity will just become 4 times, right? Because that's what the relationship is. If the diameter decreases, it becomes 1/2, then this will increase by a factor of 4 so that the effect is nullified. So let's say this is 2v naught, this is 3v naught, this is 4v naught. So at this point, I will have it somewhere over here. What if I have this 1/4? So 1/4 will make it, of course, 16. I cannot really show 16 over here at least. So I'm just gonna make a curve that looks something like this, and this will overshoot over here because we'll go right away to 16, right? So that should be the graph that we have here. The next we are given that the fluid with a density rho is now flowing through a pipe as shown in the figure 3, and as the fluid passes through the point X, where the pipe's area is A, the pressure in the pipe is Px, and the height is h, and the velocity is v. And the pipe narrows to an area of half a at a point y, which is a vertical distance 6h from the ground. So we have to write an expression for the pressure at y in terms of all this. So we have to use Bernoulli's equation over here because we're going to conserve the energy per unit volume. Okay, so I'm going to say that the pressure at x plus rho gh, that is the height at h. And is there any velocity? Yes, it is half mv square, half rho v square, and the density is definitely same, so that's not going to change. That should be equal to the pressure at y that we need to find. Then rho gh, now be careful, h is not 6h. H is not 5h, h is 6h, because 5h will just be the height from here to here, and we need to measure from the ground. So that's just 6h. And now we have half rho v, let's call it v2 square, because I don't know what v2 is. But for that, I can use the equation of continuity. I can say that a1 v1 or a1 ax vx should be equal to ay vy. What is the area at x? That's going to be a. What is the velocity at x? That's going to be just v. will be equal to what is the area at y, that's half of a, and what is the velocity at y that we do not know. So these two are gone, and the velocity will now come out as twice of what we had at x. So now this is going to look like px plus rho gh plus half rho v square will be equal to py plus 6 rho gh plus half rho 2v square, right? So this will become px plus subtracting 6 rho gh both the sides, this will become minus 5 rho gh, and 2 square is 4, 4 divided by 2 is 2, and if we subtract this both the sides, then half minus 2 is negative 3 over 2. So negative 3 over 2 rho v square, that's going to be the pressure at y. So that's the well, equation that we are looking for. Then we have to draw the bar graph at the pressure x and y, indicating the external pressure, the value of rho gh, and half rho v square. I think that's easy for us, half rho v square, because I know that the velocity just becomes double, right? Velocity is double. So if v becomes double, then half rho v square will become 4 times, because there is a v square factor here. So 2 square will just be 4. So this is drawn to 1 bar. I'll make it to 4 bars, of course. So 1, 2, 3, and 4, because relative bar heights matter. They are clearly stating that, right? Then we have rho gh. So rho gh becomes rho g 6h, because the height is 6 times, right? So if it is 6 times, then I'm gonna just mark it 6 to 6 blocks. So 1, 2, 3, 4, 5, 6. So there you go. 6 blocks is this. And then the external pressure. So for external pressure, I can use the conservation of energy per unit volume, of course, because how many bars are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, then 10, and then 11. So it has 11 bars in total. And how many have we consumed so far? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Only 1 bar is left. So this external pressure will actually just have a single bar, so that the energy per unit volume is also conserved. Finally, they are saying that the diameter of the pipe at point Y were larger than it is, then indicate whether the pressure of the fluid at Y would increase, decrease, or remain the same. That's a very popular question, actually. Whenever the diameter will increase, the area will also increase, right? And as per the equation of continuity, the velocity will decrease. And wherever we have less velocity, we have more pressure. So pressure is actually going to increase at this particular position. So our answer will be A. That's one way to do it. And another way is they are asking us to use the bar graphs from C to justify. So we can do that. Velocity decreases, right? So if the velocity decreases, obviously this bar will decrease, right? This bar will decrease. And height is not changing anyway. Height is not changing anyway. So if this bar decreases, to maintain the same number of blocks, this height should increase, right? So this height has to increase, which is the external pressure. So that's a way in which you can use C to say that the pressure actually increases.